Okay, we're looking at two boxes here strung together with a rope that's over a pulley, and this one's sitting on a table or the earth or whatever. So we'll start with the system schema. Big M and little m, those boxes. There's also a rope, and there's also the table/earth. I'll combine that as one object. The rope interacts with both boxes via tension, and that's the same tension, so I should use the same symbol. The rope interacts with the top box gravitationally, so little m times g. It doesn't touch it, so there's no normal force. It does touch the bottom box, so there is a normal force there, and there's also the weight. I will say no weight for the rope because we'll take our ropes to be massless. Rope is interacting with the pulleys and such, but we have enough to get all of our interactions for M and M. Those are the ones we care about. So now that I have my system schemas, I'll draw my free body diagrams. First for the little m, there's a tension up and a weight down. Those balance because it's in CVPM. It's not going anywhere. And for the bottom one, there's a tension down. A tension up also, and that tension should be the same size because it's the same rope. There is a weight down, and the weight should be bigger than this weight because the mass of this box is bigger. And there's a normal force up, and that normal force up has to balance this. The normal force plus the tension balance this because it's in CVPM. Depending on where we are in the term, we may or may not have talked about good directions of positive when you're using a rope. If I'm going to pick up for this box, I want to let that direction of positive follow the rope, we say. So it should be down for that one. I want to let it follow the rope because if this thing starts accelerating, then maybe this box accelerates up and that one accelerate down. We want both those to be either positive or negative, so I can either choose up for this one and down for that one, or up for this one and down for that one, but I don't want to choose up for both, because then one would have a positive acceleration, one would have a negative acceleration. That would sort of mess with our work later. In this particular case, because the acceleration is 0, it's not going to affect our result, but it's good to get into the habit now, because it'll come back and bite you later if you don't. So doing that direction of positive, I have the normal force up, I have the tension up, I have the weight down. It equals 0 because it's CVPM. Up here, I have mg down, which we've taken as positive, minus t. It's up, it's the negative direction, equals 0. I could plug in numbers and solve at this point, but I see later in the problem I'm going to want to solve it with a bunch of different sets of numbers, so I'm going to go ahead and solve it with symbols instead. Solving with symbols is always a good idea, but in this case it's really going to pay some obvious benefits. Pretty easy to solve here. The tension in the rope is equal to the weight of the smaller box. And if I substitute that result n, I can solve down here for the normal force also pretty easily. So I'm going to add that over. I'm going to subtract that over. And maybe we'll even factor out the g here. So I have my results here. I can do this with all kinds of sizes for the boxes. So in particular, I'm going to change the mass of little m. So big M is always going to be 5 kilograms. Little m is going to be 2 kilograms in the first case, which would make the tension force 2 kilograms times 10 newtons per kilogram, or 20 newtons. And that would make the normal force, this difference here is 3 kilograms times 10 newtons per kilogram, or 30 newtons. If m is 1 kilogram, then this would be 1 kilogram times 10 newtons per kilogram, or 10 newtons, leaving this to be 5 kilograms minus 1 kilogram, 4 kilograms times 10 newtons per kilogram, or 40 newtons. So if that hanging one is smaller, it makes the tension in the rope less, but it increases the size of the normal force. You can think of it as this pull up sort of relieving the normal force of having to hold up so much of the box. But if this gets lighter, then the normal force has to push up more. If that one's 4 kilograms and it's bigger, then the tension goes up to 40 newtons, 4 kilograms times 10 newtons per kilogram. But this difference now is only 1 kilogram, so that's 10 newtons. So the closer this mass gets to that one, the less the table is actually supporting this. If we go up to 6 kilograms, then we would get a tension of 60 newtons, but a normal force of negative 10 newtons, which doesn't make any sense at all. Actually, neither of these make sense. A tension of 60 newtons tells me this is in CVPM, but this being negative 10 newtons tells me that this direction is wrong, that this would actually be 10 newtons in the downward direction, and the table can't pull on the box. I don't know if it's sticky or velcroed or something, I guess it could, but just a regular table can't pull on the box, so that tells me that this is not possible. And what's going to happen is the box will lift off the table, and N will go to 0. It's because they're not touching anymore, right? Which means that the tension will be less than 60 newtons because this box is going to be accelerating downward, so the tension can't be pulling up as much as its weight is. We don't quite have the tools to calculate that at the moment, but the tension will have to be less than 60 newtons if that is going to accelerate.